L'Hopital's rule has another version. Remember, what we've already done is that if you're looking at a situation where you get the limit as x goes to c of f of x over g of x, and this looks like a 0 divided by 0, then this is equal to, by L'Hopital's rule, the limit as x goes to c of f prime of x divided by g prime of x. So instead of looking at the limit of the y values, you look at the limit of the slopes, and it ends up being the same thing. Well, it turns out that L'Hopital's rule also works when you have an infinity divided by infinity. Now, I have a couple of different ways of at least somewhat visualizing why this works. For one thing, I view 0 and infinity as reciprocals of each other in the following sense. Note that if you take the limit as x goes to 0 of 1 over x, this is the reciprocal function, right? If you plug in a 2, you get a half out. If you plug in a 5/3, you get a 3/5 out. But if you plug in a 0, what's happening? Well, let's go from the right. This graph looks like this. If I'm plugging in values of x closer and closer to 0, positive values of x, then the reciprocal is getting bigger and bigger and bigger, and this would be infinity. Likewise, the limit as x goes to 0 from the other side of 1 over x is minus infinity. So the reciprocal of 0, if you're thinking of it as a positive number, then that's positive infinity, and the reciprocal of 0, if you're thinking of it as a negative number, is negative infinity. Likewise, if you look at the limit as x goes to infinity of 1 over x, right? As x gets bigger and bigger, what's the y value doing? Well, that's going to 0. Right? The limit as x goes to negative infinity of 1 over x, right? The y value is headed into 0. So very much 0 and infinity play the role of reciprocals of each other. And so when I'm looking at an infinity divided by infinity, part of me thinks, well, that's kind of like a 1 over 0 divided by 1 over 0. And how do you divide fractions? Well, you invert and multiply. So this would be a 1 over 0 times 0 over 1, which would, of course, be 0 over 0. So the infinity over infinity is kind of like a 0 over 0. That's kind of hocus pocus, but still, it gives you an idea of how they're related. A better idea of why this would work for the infinity over infinity situation is that when you're taking a limit, actually, in the situation I'm thinking of, this doesn't even have to be the limit as x goes to c. This could be the limit as x goes to infinity. You know, I'm thinking of two functions that, you know, are, as x goes to infinity, they're headed off to infinity here. And after a while, and you get way out there, you can't see the axes. In fact, I'll get the axes off. And you want the ratio of the y values, this y value divided by that. That's the limit you were doing to start with. And I'm claiming you can do the limit of the slopes, saying that after a while, the difference between the y values is not going to matter. It's more a matter of what's the ratio of them. So if this is headed up like a line of slope 3 and this is headed up a line of slope 2, this will essentially be 3, you know, in a ratio of 1.5 times as big as that one, because they're both going to be huge, but this is going to be going up with slope 3 and that's going to be going up with slope 2, and so this one will be about 1.5 times as big as that one. And the bigger x gets, the closer that will be to actually, you know, 3 divided by 2 would be the ratio. When you let's do an example or two here. Limit as x goes to infinity of 3x squared plus 5x plus 7 over 2x squared plus 8x minus 5,000. Actually, 1,500, because that's what came out. You know, back in even in a pre-calc 2 class, you would have, or pre-calc 1 class, when you're looking at rational functions and horizontal asymptotes, you make the argument that, as x is headed to infinity, really the only thing that matters is the biggest power in the numerator and denominator. So you just cover up the rest of that stuff and say you're looking at a 3x squared over 2x squared, which looks like 1.5, right? And that's the correct answer here for this limit. There's a horizontal asymptote of 1.5. From the point of view of L'Hopital's rule, we can see why that biggest term is the only one that matters, because as I do L'Hopital's rule, this is an infinity divided by infinity situation, right? As x is going to infinity, both these quadratic functions are headed to infinity. And if I look at the derivatives here, I've got 6x plus 5 over 4x plus 8. And you can see that the constants really don't have any effect anymore. They're not even represented here. Whoops, and I'm still taking the limit of this as x goes to infinity. And I'm still in an infinity over infinity situation. So let me apply L'Hopital's rule one more time. The limit as x goes to infinity of the derivative of the top there is 6, the derivative of the bottom is 4. This is now not an infinity over infinity situation, but so plug the infinity in for x, but there aren't any x's left, so it's just 6 over 4, which is 3 over 2, or 1.5. So you can use L'Hopital's rule here in this infinity over infinity situation. Now, granted, that may have been easy enough to do even without it, but it works. There's an example I want to take a look at here. The limit as x goes to infinity of 3x plus sine x over x, let's say. Keep it reasonably simple. This is an infinity over infinity situation, so I'm going to try L'Hopital's rule on it. Limit as x goes to infinity. Derivative of the top here is 3 plus cosine x. Derivative of the bottom is 1. Now, if I look at what happens as x goes to infinity, well, this just looks like 3 plus cosine infinity. The problem here now is this function, as x is going to infinity, is a cosine curve up here going back and forth between, it's 3's in the middle, so it must be between 2 and 4, and there isn't a limit, right? This limit does not exist. And this is one thing that I want to point out here, that L'Hopital's rule says if this limit exists, then it's the same as that one. But if this limit doesn't exist, it doesn't tell you anything about that one. And in fact, this limit definitely does exist, because I can think of this as the limit as x goes to infinity of 3x over x plus sine x over x, right? This 3x over x, that's just going to 3, and the sine x over x is going to 0. Why is it going to 0? The numerator is bounded between 1 and minus 1. The denominator is getting really big, so you got essentially a really small numerator divided by a big denominator. That's going to be 0, and so this limit here is equal to 3. Right? So I show this example because L'Hopital's rule says if this limit exists, then it's the same as the one you started with. But if this limit doesn't exist, it doesn't tell you anything about this one. You got to go back and find another way of doing that limit. Okay. All right, 0 over 0, infinity over infinity. That's when L'Hopital's rule applies.